Welcome back. This is video part 2 of video notes 54. We were talking about some realistic uses or ways that we could use similar triangles to help us solve some problems. The next problem is kind of a typical survey strategy. So a geologist wants to determine the distance across the widest part of a nearby lake. The geologist marked off specific points around the lake so that the line containing DE would be parallel to the line containing BC. The segment BC is selected specifically because it is the widest part of the lake. The segment DE is selected specifically because it is a short enough distance to easily measure. Okay. The geologist sketched the situation below. So as you're going through this, one thing you would want to make sure you understood is that DE is parallel to the line containing BC. And you may even want to mark that off. And so you can remember. Now, why might we want to know that the two lines are parallel? Well, there's a lot of nice results once we know they're parallel. One being that corresponding angles are congruent. And if I'm thinking about this in terms of similar triangles, that gives me enough of the information because A is congruent to A, and if the angle above E is congruent to the angle at C, then you're able to, by angle, declare that we have a similar triangle. Some other really kind of important words that are in here are the descriptions of why you're even doing this. They want to find the widest part of the lake. So BC was selected as the widest part of the lake. DE is specifically short enough that it can be easily measured. Okay, because when you have measuring tools, like a tape measure, you have a limited range of what you can do with them. Okay, and so has the geologist done enough work so far to use similar triangles to help measure the widest part of the lake? We kind of just described it pictorially. Let's make sure we put some words to it. So yes, the two triangles share an angle A, and since the lines DE and BC are parallel, BC parallel to DE, corresponding angles are congruent. And then therefore, by angle theorem, triangles are similar. So that's well written. Now, description, yours might be slightly different, but you want to make sure you have all the important parts, such as the sharing angle or really the reflexive properties. So we'll just make sure that we do that. And then the description of the corresponding angles being congruent because of lines being parallel. And so then they give us the distance of DE. So DE is 5 feet. And remember, DE was that manageable distance. AE, they could also measure, is 7 feet. So we'll put the 7 there. They tell us that EC is 15 feet. Does she have enough information to complete the task? She does, because you can compare this sort of bottom left-hand side to the 7 and then the 5 to the distance of BC. In other words, I can set up the ratio AC over AE equals DE over BC. That's one way to view it. The other way to view it would be how I color coordinated it and do something like AE over DE must be in proportion to AC over BC. And so that's 7 over 5 equals AC. Oops, sorry, AC is 22 over BC. And as you solve it, you have 7BC equals 110, and then BC has a length of approximately 15.7 feet. All right. Next question is kind of interesting. It says, assume the geologist could only measure the maximum distance of 12 feet. Could she still find the distance across the widest part of the lake? And as you're looking at that, a lot would depend on how you're able to set up your parallel lines. And so obviously EC at the moment is 15 feet. She would have to reconstruct triangle AED to shrink EC to a maximum of 12 feet. And since they don't give us specific distances, I can't give much more detail, but potentially you'll have to shift the type of triangle that you have, maybe to go from here to here, and then shift point A so that then you can draw the line through this point to this point. There's ways to do it. You just have to rethink the way you're constructing your triangle. Okay, finally we have something that sort of relates to you guys here in California. The world's tallest living tree is a redwood in California. It's about 370 feet tall. In a local park, there is a very tall tree. You want to find out that if the tree in the local park is anywhere near the height of the famous redwood. So we have redwoods nearby. Something as close as Redwood Park up near Oakland has some redwoods. They're not obviously this famous 370-foot tall one. You also have Muir Woods. So I included this problem more for the realism of how it connects to your lives. And so as we look at this, we have triangles. The question is, describe triangles in the diagram and explain how you know they are similar or not. The triangles are basically from the top of the tree down a perpendicular distance to the ground over to some point O. And similarly, you have your person standing here. We measure the height of a person from the top of their head in a perpendicular distance to the ground. And so because I have two right angles, plus I have the shared angle ROD, by angle, they are similar. So then they say assume ESO is similar to triangle DRO. A friend stands. And so the assumption is actually important, because when we assume the triangles are similar, we know that side lengths are proportion and the angles are congruent. A friend stands in the shadow. He's exactly 5.5 feet tall and casts a shadow of 12 feet. So this person is 5.5 feet tall and his shadow is 12 feet. Okay, is there enough information to determine the height of the tree? And right now we actually do not. because really all I have is the information about the person in their shadow. I don't have any information about the distance the person's standing from the tree. I don't have any information about the height of the tree. So what I would need, we need information about the shadow. Okay, your friend stands exactly 477 feet from the base of the tree. Given this new information, determine how many feet taller the world's tallest tree is compared to the one at the local park. And so, if my friend is standing 477 feet from the base of the tree, that would go between the distance of R and S, and then the total distance of SO would equal 489 feet. And so we can use this now to set up all the formulas that we need. So 5.5 over 12 is equal to the unknown over 489. Use your trusty calculator. 5.5 times 489 is 2,689 and 1/2, which is equal to 12x. I divide 12 on both sides. And let's be honest, this tree is super tall. The tree is approximately 224 feet tall. But that's not actually what they asked. It said how much taller. So I really have to take the 370, subtract off the 224. And the redwood tree is 146 feet taller, which is huge. Okay? Assume your friend stands in the shadow of the world's tallest redwood tree, and the length of the shadow is now just 8 feet tall. And the reason why that happens is if you come up here and you raise the point of the height there, the shadow comes at a steeper angle down to the person, which shrinks it on the backside. But we're going to do that calculation. And so I have 5.5 divided by 8 equals 370 feet over the shadow size. 5.5 times the shadow is 2960. Divide both sides by 5.5. And you get 538 and a repeating 1800ths. So the shadow of the redwood is approximately 538 feet long. Okay, so again, these are realistic uses of similar triangles. Survey specialists oftentimes use these strategies or build upon them for more advanced tools. But just be aware that there is potential uses for the math that you're learning. Thank you for your time.